So now I should introduction slides, right? I see. Okay. Now, if I have to bring up the introduction slides first, I should remove mine, I think.
Yeah, correct. I think so. Sharon, if you have these slides, I think probably you can also project. Then
Yeah,
later
you
can switch control to him.
Yeah, I can do that, sir.
I think Vijay has left, I think, and he has to relog again.
Okay. Are you able to see my screen?
Yet to. I think yet to come. Yeah, now it is fine.
Now you're able to see the introduction screen, intro slide.
Just check Vijay is already there.
Yeah, I'll check, sir.
Because I think he has left.
Oh, is it?
Hmm.
Just a second.
I'm here. Hello?
Yeah, now he has
he's
come.
here, sir. He's here.
Yeah, he has come. Okay.
Yeah. Vijay, sir, shall I go ahead, sir, with the introduction?
Yes,
Yeah.
go ahead. And do you see the slide?
Then in that
Yeah,
case, you
I'm able to
remove
see the slide.
your
Yes,
slide.
yes. Yeah. Let me take control, sir. Let me take control.
Jayagaran, I suggest you mute everybody and allow only Vijay to talk so that there is no background noise.
Yes, sir. Yes. Yeah. So very good morning, all of you. Thanks for joining another session of ISA South India section. As before, the COVID-19 is posing a lot of challenges to the entire world, and people are seeing ways of doing business in a different way. So, in fact, we also wanted to conduct this session as a seminar, but we ended up in a webinar. And thanks to the new technologies like Microsoft Teams, which is making such things happen. Okay, so this session is going to be on edge computing, a new technology which is upcoming in the IT field, and how we are going to adopt that in the industrial automation field. Okay, I'll go back to some of the quotes of the popular automation futurist, Mr. Jim Pinto. He used to say that the automation field doesn't have a technology on its own. It always adopts the new technologies, upcoming technologies in the IT field into the industrial automation, because industrial automation field per se, if you take, has a lot of old technologies, but there is no much of innovation in terms of the industrial automation field over the past few years. But the good thing is that whenever there is a new thing coming up in the IT field, we always try to adopt in the industrial automation field. One such revolution which happened is the adoption of personal computers in the industrial automation field. And right now, we are in a stage where we are trying to adopt the new technologies like cloud computing and edge computing into the industrial automation field. So there are some ground rules for the webinar. I request all of you to switch off the video and mute yourself during the session. So this will save a lot of internet bandwidth. We would also request the follow the presenter's flow and reserve your questions at the end of the session. And whenever you have a question during the Q&A session, please unmute yourself and post your question and then mute yourself again. I'd like to invite Mr. Sai Ramesh sir to give a brief of about our ISA session, sir.
Good morning, everybody, and welcome to this webinar on edge computing. And ISA South India is one of the pioneer in India. More than 26 years of existence, and ensuring that the community of industrial automation and control gets updated. You know about ISA. If somebody is not aware of ISA, it is organized. It's an international society for automation, for instrumentation and automation professionals. And ISA is organized geographically, and 150 sections are there throughout the world. And actually, it is one of the main purposes to create standards with the help of the professionals themselves, so that worldwide it can be used. And there is one of the major advantages is there is a good amount of networking possibilities. If you are a real actually need of anything, you can meet these kind of people who can give you solutions, and they can also share their experiences in dealing with issues and problems in process control and automation. And one of the, I said already, one of the oldest sections, completed 26 years. It's a good blend of academicians and industrial specialists, actually professionals. There are 4 doctorates in instrumentation engineering in South India section, and there's a very wide, diverse industrial specialists, basically petrochemical, cement, pharma, wastewater, and other verticals. And you have an IT, OT domain space specialist also. And there is a rich experience, young workforce trying to work together with the senior level professionals and academicians. With these few words, I will hand over to Jayaharan and Mr. Vijay to continue. We do not want to waste our time on this. Thank you very much, and we welcome you all to be part of ISA South India whenever if you think that it is helpful for you in terms of your professional growth. Thank you.
Thank you, Sai Ramesh, sir. I have 2 more slides. I'll just quickly skip through.
Yeah.
We we in ISA South India have many firsts. Out of this last webinar, we are able to generate an e-certificate for all the participants in the webinar. And the latest of all these things is we now have an international speaker for the today's event. Mr. Vijay Rangarajan is connecting from USA, and we are sitting in India and Singapore and other participants going to listen to him. I'll give a brief introduction about Mr. Vijay, who is a very senior person. He graduated from REC Trichy and did his master's from University of Minster. Mr. Vijay has demonstrated proficiency in reshaping IT-driven manufacturing management, development, and execution of the connected enterprise and smart manufacturing. So he's able to solve complex problems in manufacturing using modern technologies like IIoT, AML, MES, robotics, and automation. He's always passionate about integrating the plant floor and to the business floor and getting some real insights out of the manufacturing domain, manufacturing floor. So that is his passion, and he has a very diverse experience in R&D execution, in working with major automation majors like Rockwell, GE, and currently he is associated with a company called IoT Co. LLC based in US, which is working on cutting edge technologies. So we are proud to have Mr. Vijay here, who has a diverse experience. Having come from a mechanical background, he has really transformed into a industrial automation specialist, and now he's working on cutting edge technologies like IIoT, AML, and things like that. And to us, I think this is not going to be a presentation. It's more of Mr. Vijay's experience. That's the reason we have named this webinar as like evolution of edge computing in industrial automation. So Mr. Vijay will be taking us through experiences, what he has gone through, both good and bad, whatever lessons he has learned. It will be a platform where he will be sharing his experience, and we'll be all listening to him in the next 1 hour. Over to you, Vijay sir. Thank you very much, everyone. Once again, welcome all.
Okay, thank you very much. Good morning, everybody. Good morning from Los Angeles. How is everybody doing today? Saturday, being a Saturday. So I know that you are all muted. So
Good morning, sir. We're all fine.
All right. Hang
Good
on.
morning, sir. Good morning.
I'm going to bring my.
Good morning, sir. Nice to know you.
Good to know you too. So hang on just a second. Okay.
Good morning, Vijay. It is really a pleasure to listen to you with such a senior person with experience. We look forward to get your hands-on, and also, as Jayaran said, how we can apply it in India and Singapore. Some of these contexts are there, but how we can learn from you and how we can apply it in our context.
No problem whatsoever. Okay. Hang on just a second here. Upload from my computer. Should I just do it from my desktop or upload? What do you think? I think I'll just try from my desktop. Okay.
The screen so that everyone can watch.
Yeah. Has the slide come up yet?
It's come up really well, sir. Yeah.
Yeah.
Okay. All right. I've got the presenter's view over here. You are just seeing the main slide, right? Not the presenter's view.
No, I think we are seeing presenter's view.
You are.
Yeah.
Okay.
I think you need to go for.
Okay. Hang on just a second over here.
Yeah.
Click those three dots and you get the.
Yeah.
Yeah, this one.
Hide presenter view. Yeah.
Yeah. Correct.
Yeah.
Yes, sir.
That's yeah.
Okay, we've got the full screen now. All right, evolution of edge computing and industrial automation. So I won't waste too much time on the subject. Actually, like Jayaharan said, it has been an evolution, and I have been in this field for over 40 years. So, what is the definition of edge computing? Now, in the word evolution of edge computing in industrial automation, you've got the word edge computing, and also you have industrial automation. So first, let's take a good definition of what is this edge computing that has been, brought about more recently, and industrial automation. What is that? Let's take a look at that. So if you were to look at what the dictionary says about the definition of edge, again, it depends on where you stand. The description in the dictionary is the outside limit of an object, area, or surface, a place or part furthest away from the center of something. So in other words, The edge depends on where you stand. So bringing it to the context of our subject topic today, the edge for IT people is a certain place, and for the edge and the edge for the manufacturing folks is certain, other place. So let us see, what this is. So where is the edge? It all depends on if you're an IT software engineer or a hardware engineer or a mechanical or a process engineer. Uh, what you see as the edge is going to be different. Okay. So let's dive into the meaning of what is industrial automation. Industrial automation is use of control systems such as computers or robots and information technologies for handling different processes and machineries in an industry. I won't read this, okay, because you can read it quite nicely. Is the speed okay when I move through the slides? Is it coming through quick enough?
Good, sir.
Good, sir. Good. Yeah.
Okay. Now, industrial automation by itself has gone through an evolution. First, it was fixed automation, primarily with the relays and so on. Then came the programmable automation, and then it has moved into flexible automation. And from there, with the use of IT, like Jaiharan said, it is moving into yet another transformation into industrial Internet of Things, where machines are beginning to talk to each other. We will look at that a little later. So continuing with the evolution of the automation, I said fixed automation was managed with relays, starters, basically discrete devices, and there was no ability to change them if something had to be changed on the line. A process change happened. It was extremely difficult, and these relay panels were huge. So right around the 70s or the actually the mid 70s or so, GM issued a specification for coming up with a programmable automation, basically programmable relay panels, because they were tired of replacing these relay panels every time there was a model changeover. And the company by the name of Modicon was the one who was given the specification and requested that they come up with uh, a computerized or a programmable, controller, which would be able to make the changes on the production line whenever there is a change in the production line, and it didn't have to amount to massive changes on the relay panels. Okay, so that was the introduction of the PLCs, the programmable logic controllers, way back in 1970s. Then came the flexible automation side of things, and here the computers were the ones who got into the act of the flexible automation. So here, primarily using computers and displays and other programming terminals, we were able to produce very different styles and many different options and so on for whatever you were trying to manufacture. And a good amount of flexibility you were able to gain simply because of the ability to change what was going on the line on the fly. Then finally came the communications and the networks in industrial environments. The PLCs in the beginning, they did not have any ability to talk to each other, but the need came as people started to use more and more. Uh, Companies wanted to connect different islands of automation. So the PLCs had to be connected. So communications had to be developed. First, of course, the first communication was a direct wire communications. And next came the RS-232, primarily developed for IT, and it was used in the automation too, but the reliability and the number of pins and so on was, too high. And of course, I don't need to go through the details of any of those things. I'm just going to be talking about that because all of that is 40 years ago, but I need to prepare the groundwork for where we are today and how things have come up. And then communications networks, okay? Here, there are so many different communication protocols and so on. And the confusion for everybody is, why do we need this many communication protocols? Again, each one of them were developed for a particular criteria and for the case on hand. In other words, field bus excelled in a certain, certain types of environments. When I say environment, I mean to certain types of automation and so on. Control net, again, for remote IO, that was developed by Rockwell. HART communications, highway addressable remote transmitters. And again, the protocol for HART was developed with a particular device and devices in mind, especially when they were in remote locations, where in the middle of the desert, and the distance to the valves and such things was too high. So, in other words, communication protocols were developed for each particular situation on hand, and as time went by, they improved more and more and more. And today, everybody understands Ethernet protocol, and I think a lot of the younger folks may not even know that the names of some of these field bus and Profibus and control net and a whole bunch of other protocols. Basically, don't get scared of computer protocols. It is just like a person who knows Tamil talking to somebody who knows only Telugu. How do you talk to him and convey your messages? You will have to get somebody in between, an interpreter who knows both sides. And this is what the devices like gateways do today. But if the vocabulary of the Telugu guy who speaks only Telugu, he knows just a few of the Tamil words, and if there is an agreement between both, I will use only the few Tamil words that you understand. Now that becomes a separate protocol. Okay, so all the communication protocols operate in that manner. Uh, so anyway, I will continue to the next one. Okay, so as time went on in industrial automation, the need for data processing was rising early 80s and 90s. And what was happening was the concept of the cell controller was taking root in many corporations and companies and so on. So the cell controller primarily is something that shared data between multiple automation locations. Basically, different PLCs were controlling certain areas, and the data that was required from one to the other, instead of a lot of communications going back and forth between different PLCs, they all came to a central controller, and that parsed everything and gave it to the individual PLCs controlling different locations. So basically, that was one of communications and data processing. And also the scheduling and things such as MAPIX and COPIX for the manufacturing software they were entering the shop floor. And all of that required a computer, to be used in the manufacturing floor. But again, computers were not industrially hardened those days. The first hardened industrial computers were the microvaxes. They were released for manufacturing, and subsequently, Rockwell had a microvax in the same chassis as a PLC. And that was the first instance of an edge computer. Basically, edge computer sharing data over the backplane of the chassis, in which a PLC was there. And subsequently, Rockwell followed with a PC instead of a microvax. When the PC became a lot more popular, it was on the same industrial DAC with a PLC, and slowly the need arrived. The need was increasing on a daily basis to have data processing capabilities. Next, and this is just a news report. Okay, Kraft drives vendor integration efforts, and this was from Computer World way back in 1991, 30 years ago. The need was there then, and the need is here need is there even today for integration, of different systems, communications, computers, PLCs, the whole works. Okay, let's look at an example of automation with robots. And here, I'd like you folks to focus on how the robot moves around and the points at which the spray starts and the times when it closes the door, opens the door, and basically how both, that is, the robots on opposite sides are synchronized. And right after this video, which is about, I think, minute and a half or so, I will talk about the systems approach to how the automation was approached, for these painting robots. And by the way, the principles, design principles used at that time is still applied even today, except today it is a lot easier because your programming languages and all the tools that you have available makes it a lot easier. So let's see what happens when I, can you see it?
Yes, we are able to see.
Robotic bell painting system for a major Midwestern truck manufacturer. Flexibility, versatility, and
By the way,
non-obsolescence are built into the twin
this is my entire design. I started with a clean sheet of paper when this project started. It took me 1.5 years to have the robots running like you see in the video. Or not.
Is the audio muted, sir? We are not able to hear anything.
No, that's okay. It's pretty low. There is an artifact tag reader. There's a verification of the artifact tag. So match it. Close the door. Okay. So I hope the video came through properly.
Yes, it did, sir. Yeah.
Okay. Excellent. All right. I just wanted to make a few major points from the video. Okay. So the different subsystems, of the painting system was you had the robot playing a path for each particular style. What that means is automatically the robot controller should pull up the correct path based on the correct style of the vehicle. Otherwise, it might hit the vehicle. The next is the paint applicator. Every time it needed to paint, it was triggered on and then triggered off, and then triggered on and triggered off, and it goes through the entire paint path, with what we call as the paint parameters, and that is a separate system. And then you have the conveyor and the booth air, and these are the peripheral systems. Simply, I'm just making, in order to keep it simple and quick, 3 systems, and this had to be coordinated precisely because the robot is moving at 4 feet per second. So what that means is, in half a second, the robot has moved 2 feet. In 250 milliseconds, it has moved 12 inches, 1 foot. So the scan time of the PLC, because of the enormous amount of programming it had, including a lot of data processing the PLC was performing, it was over 250 milliseconds. So what used to happen is, each time you trigger the robot, the trigger would come on at different locations, and that was not okay. Each time you trigger, the trigger must come on precisely at exactly the same location. And not only that, there are pneumatic delays because this is a paint spray booth. It is a class 1, division 1, explosion category. So everything is pneumatic, and the pneumatic system introduces its own delays. And coordinating all of that was one pure hell. So what we learned in this particular project was control of timing was critical. And the only way that we could do that was to have a very tight coordination between the computer, which managed, all the paint paths and parameters and so on and everything else, and the PLC performing its control for automation. In other words, the PLC, it performs the IO scan and then the program scan, the IO scan and the program scan, and it is highly predictable. So that way you could do coordination in a very precise manner. So therefore, the first pyramid integrator from Rockwell was the first PLC, which had this extremely tight integration with the computer and a PLC. It was a microvax in the same chassis, common backplane, and it had an Ethernet port for external connections, all in a rugged industrial chassis, and the whole package could be deployed in a shop floor. Okay, and by the way, you guys can't even guess what was the year in which I deployed that computer-based robotic system. That is a PLC-based robotic system that you just saw. This was way back in 1991. I don't know how many of you were even born at that time. Probably not. Some of you were born. A lot of you were not even born, I think. But anyway, let's move on. So some of the early attempts at an edge computer was people trying to put a computer with real-time operating systems in a VME bus. Again, VME bus, Versa Modular Eurocard bus. This was a backplane, a passive backplane through which communications can happen, and it was very successfully deployed in the military because it could survive very harsh environments, particularly vibration and so on. And some of the Air Force, that is the U.S. Air Force had pretty much everything that was VME bus based. And those were the early attempts at having a edge computer, sitting right there on a backplane along with the VME bus based PLC. And again, another picture of a PLC and a PC coexisting in a VME bus. And by the way, a lot of companies, were able to take this particular packaging and deploy edge-based computing out on the shop floor. But it was not called edge-based simply because, the guys in manufacturing they just approached it as a problem to be solved, and they didn't care much about giving it a classification. So let's see. So the next thing that happened in PLC communications again was protocols, right? You had a lot of companies coming on the bandwagon with their own proprietary protocols simply because they said that, okay, we have addressed communications in the best way possible and ours is better. So I'll just quickly play a minute. Yeah. Okay. The point I wanted to convey was the fact that you are talking about real-time communications when it comes to automation. And for real-time communications, you absolutely must be able to do it in a very predictable manner. And Ethernet has taken hold in a very big way, even in automation. Even though Ethernet is not a highly predictable protocol, because of the speed with which you can uh, connect different devices, the speed has gone extremely high to 1 gigabit per second, even in plant floor communications. So you do not see any latency, lag, or any such thing. So therefore, PLC communication simply has become a standard in a lot of different IoT applications, as well as Ethernet IP. And of course, there are mechanisms to make it deterministic. Uh, when Rockwell has modified the Ethernet IP to suit their IO communications. Okay, so again, the major points to remember in automation and the evolution of automation is the fact that data communicate the requirements for data processing was increasing as automation was increasing, and data and computers were evolving on the IT side at a tremendous pace, and the usage of IT and its application capabilities and the integration and so on was lagging behind in automation. And let us now jump to the evolution of information technology, on a parallel basis that was also going on while the automation was happening on the shop floor and instrumentation and so on. Okay, so this is a very quick summary of what was happening in terms of evolution on the IT side of things. You had the age of mainframes back in 1960, Then came the microprocessors and the controllers in 1970s. I remember one of my projects in my master's was to program a microcontroller that is an 800 microprocessor along with other external memory and so on to simulate a lock, a digital lock. Okay, that was a fun project to do. This was way back in 1977. Then came the mini computers and then the PLCs in the 80s. Of course, the PLCs did use principles of the computers. Of course, inside the PLCs, the same large-scale integrated IC chips were used, and the principles of a CPU, writing to memory, reading from memory. Of course, all of that was highly industrialized environment, and they could survive temperatures of plus 50 degrees Celsius. Then came the PC and the internet revolution, 1990s, and that was what changed the entire trajectory of things moving fast. Communications then, the communication standards and everything else improved, to such an extent that people owned their own PC. It was extremely inexpensive, and the connectivity was established using simple browsers, and the power of the internet was put to use. Of course, the internet was already there. I was actually using the internet way back in the 70s, but it was at 300 baud, teletype machines, and only connecting to different universities. And the PCs and the internet revolution, 1990s, that is what made it all possible. And then the communications in the around the 2000s, the Y2K and so on, that really brought about an explosive growth in applications and so on, simply because that also opened up the IT revolution in terms of ERP applications and so on. So a lot of companies from overseas and in the United States participated in it, in the development of standards, and different industry verticals like banking and oil and gas and automotive jumped on the bandwagon. Primarily, it was all in IT. And finally, now we are at a stage where there are a lot of tools for developing applications, and interoperability of technology stacks is the quest right now. And depending on whose technology stack we use, again, I'm using terminology here. I don't want to dive into defining what technology stacks are. It is just a collection of a bunch of people's databases, OSs, and a few other things, which operate together very nicely. And any enhancements of one will not impact, or it is taken into account by the other very quickly. So the technology stacks, there are a few which compete with each other. So the 2020s, that is what interoperability is going to be the issue. And by the way, interoperability at the program level, we already have that at the data level. Okay, and the way they do that in the most simplistic manner is one software writes into a certain bunch of locations, another software reads from it, and somebody else writes into another location, and somebody else reads from that. As long as everything is all documented and upfront, things work properly. But things all go nuts if somebody makes a change and it is not disclosed to everybody else. So there are a whole host of issues like that in the IT side of things. But whereas if a program and objects and such other things can be executed in one stack versus the other stack, things will be a lot more stable. But anyway, there is a lot of detail I would have to get into that, but this is enough at this point. So let's go down one level and see in the evolution of IT, how did this come about? So I'll start with 1970s. the Intel 4004 1971 microprocessor, and then came the Intel 8008. That was the first microprocessor in competition with Motorola, which was the MC6800. The picture you see here, you can't make any head or tails of this, okay? But the point I want to make is those were the first days of what we call as the large-scale integration of transistors and so on, whereby this is just this is smaller than a thumbnail, and there probably has 1,000,000 transistors, okay, and other devices on this. It has the complete elements of a computer, except it doesn't have enough memory. All the RAM and everything else had to be, have to be externally added in order to make it a computer. But the real processor which came into a PC was the 8286. Okay, so what was happening in the computer industry was that they were shrinking in size. Each processor was shrinking in size, and they were doubling the speeds at which the computations were happening. That was called as a Moore's law, just to simplify things, okay? So the simple rule of thumb was you reduce something in size, it increases in speed automatically. There's no magic there. So all the effort was in size reduction, and they were able to do this with a lot of lithography and such other methods, okay? And by the way, just a quick math over here. Speed of light is 299,792 and 458 meters per second, okay? So approximately, if you say that that is 300 million meters equals 1 second, then 300,000 meters equals 1 millisecond, then 300 meters equals 1 microsecond, and 30 centimeter equals 1 nanosecond, okay? The analogy here is, let us say that the Intel 4004 processor, when it executed, an instruction, it took 1 second. So what that means is the signal traveled 300,000 meters inside that Intel 4004. Now, if as you shrunk the size of the processors, and let us say that you are able to execute an instruction in 1 nanosecond. So what that means is the signal, an electrical signal for executing an instruction, the total distance traveled in the IC chip was only 30 centimeters. That was 1 nanosecond, 1 billionth of a second. So making things smaller is how they have made it faster, but they are hitting the limits of being able to go down smaller, because in copper, etching copper at such small levels, you can go down to 1 atomic, thickness of copper. After that, what is going to happen? Plus, the behavior of some of the materials at such small widths gets into areas of quantum mechanics. They behave quite differently. So we are hitting the limits of that, limits of speed and such things, but they are also approaching it in a different way, which is parallel processing. You break the problem into different pieces, and you solve the problem in parallel. So anyway, I won't go any further into those aspects. Then came the browser wars. After the speeds of the speeds of the PCs increased tremendously, now came the browsers, because browsers are what made the internet, possible. Basically, the browser brought everything into a nice, simple framework for a user. Interacting with the browser was very easy, and along with that, the PCs had the Windows, operating system that had a mouse option, and the rest of the story. Okay. So, circling fully back to what the edge is, This is the picture of the edge. You have a whole bunch of IT people. I call it as, the world of the IT and ERP, standing on one side of the IT and operations divide, and then you have on the other side an operations technology, which is the plant floor, where the people who reign supreme are Rockwell, Siemens, Schneider, GE, Emerson, and a whole bunch of others, okay, whose emphasis is on real time. And the world of IT and ERP, their emphasis is on completion, means they are not necessarily that concerned about anything executing at millisecond levels. So this has to be somehow bridged, which we call as the IT-OT divide and or the IT-OT chasm. So how do you do that? You do that by making things faster and standards-based approaches, as well as everything should become fast, bottom line. And if that happens, IT slowly can bridge the chasm and start to apply, the many things in the manufacturing floor. And in fact, IT world was opened up by people from India, from TCS and Infosys and Wipro. They added some phenomenal applications to the IT world, and that is pretty much exhausted now. Everybody is turning the attention now to the plant floor. And by the way, the emphasis on the IT side was always the interaction was with a human being. And at the most, they may have interacted with a few barcodes and such things, in checkout counters and such other things, but never to the extent of, I/O in the plant floor and machine-to-machine communications. People in the plant floor are quite used to that, but IT people, they are not used to it, and therefore there is a cultural angle to this. Plus the fact that operations technology folks or the manufacturing floor is dirty. Plus it is hot. Again, I've seen this in India, and I see it here in the United States. Nobody wants to come and work in manufacturing. In fact, I was having a conversation with the vice president from Ford Motor Company. He said the turmoil he goes through every time is the people they recruit for process engineers to run the line. For example, that paint shop I showed you, the robot painting the cars. The entire paint shop is run with 2 process engineers, just 2. And when they come into the shops, they are overwhelmed by what they see, and they quit within 6 months. So there is a enormous problem about having the people, and the right kind of people working in manufacturing to actually bridge the IT-OT divide and start to use IT, type applications and so on. In other words, edge computing. So what is this chasm between IT and OT automation? And yeah, I already talked about some of that. Basically, it is about real time versus non-real time, cultural differences, and again, the attitude towards a software bug. Software bugs are treated a little differently in IT versus in automation. If you had a bug while that robot was playing back, you would destroy one of those guns on the robot, spray guns. That was a $25,000 single piece, $25,000. You would, break the guns into pieces. So there was no room for error. Everything had to be tested, and it had to be tested 100%. And because it was an immediate consequences, in IT, people generally don't see an immediate consequence. You'll have your production servers, running, and you'll have your test and development servers. Everything would work nicely. Move it to the production server. Something happens. You move it right back into your test and development server, and you move the old one back into production servers, and continue on. And people, that is again, the cultural angle is something that needs to be addressed, and maybe something that will come into play in India as the proliferation of automation and IT, happens more and more. I've seen that at Mahindra and at Tata Motors quite a bit. So, from an IT view, what has changed today? Computers, they have become very powerful and inexpensive. Memory is dirt cheap. You can buy 500 gigabytes of memory in a small little USB stick, and it costs $5. Now, machine I/O can be sent directly to computers in the cloud. Okay, and how do you do that? With appropriate gateways and appropriate edge devices. But you cannot process machine I/O and send it back for control. That day has not come. But a near real time is possible now. I have seen, examples where if you have a latency of less than 80 milliseconds, and in many places here in the United States, you can get that quite reliably. Some levels of automation is possible. Network protocols like Ethernet, TCP/IP, they have pretty much standardized this across the board, and standardization is good. And in manufacturing also, the speeds at which you can collect I/O and process that even with Ethernet networks is extremely high. So you do not see any impact because of that. Sensors are becoming a lot more intelligent, and that's because they have, controller capability built right into it, and they don't need to connect to PLCs. They can go directly to the cloud or to an edge computer or to any other networks. Multiple ways of connecting with sensors these days. So in other words, today, you don't need a PLC for the kind of data that you need. You can collect them directly from smart sensors, and it could bypass the PLCs and go straight to a cloud-based, approach. And again, people like Azure, Microsoft Azure, AWS, they push, the idea of cloud-based computing quite hard. But for manufacturing plants, something intermediate, which is the edge-based computing, power, is necessary, and that is not going to go away in the near future. So, okay, age of communication standards. I talked about this already. So, what has happened is you have had technology, improvements in IT, which has slowly permeated into the factory floor. PLCs also have the power of direct Ethernet communications, and they can, do a fair amount of data manipulation, but you wouldn't want them to do that simply because of wanting to maintain the real-time capability. And drop in price of RAM memory. See, this is very critical because of this, you can execute the entire databases in RAM in your servers and PCs. And what this has done is basically you can have all the different applications running in RAM. It does not need to hit disks. So if you remember, what was DOS? What did DOS mean? DOS meant disk operating system. Disk was a very integral part of the CPU and the entire computer. Not anymore. And the disk was the one that slowed everything down, and it also was a major area for failure because it had mechanical moving parts. So if you were to combine the different technology improvements, communication speeds and standards, and operating systems, you see now, 30 years ago, there was a need for real-time operating system because standard Windows did not operate like a real-time OS. What that meant was interrupts coming in from the field. The CPU did not stop what it was doing and service the interrupt. That was Windows. But real-time operating system, there was a thing called RTOS or Linux. I think Linux had a mechanism for configuring it as a real-time operating system. They could stop whatever they were doing and they will service the interrupt. When I say service interrupt means something that comes from another machine or a switch or something, sensor that needs attention immediately. That is real time. Okay, so combining all these things together, you have enormous power available, and because of that, edge computers have come of age right now, and they can practically handle any type of data processing you need for manufacturing floor, and that too, the amount of data that is generated on the manufacturing floor is enormous. People don't realize how much data gets generated. Way back 1991 in that robot video I showed you, for every style of car that was painted, the amount of data that was being generated was 0.5 gigabytes. So imagine, a day's worth of production, how much we would have to, store, and how much of it was to be used for, analysis and so on and whatnot. But all that, we couldn't do it those days. But today, everything is possible. Okay, the resulting benefits. I did talk about the benefits. It can address large RAM memory. The SAP's HANA is an example of that. We always used to talk about SAP couldn't handle real time because of the fact that, disk operating system and such other things. Just a few years ago, we were talking about those things. But now, even an MEA system running in SAP is extremely fast. This thing about not being fast is something that we are not able to use against those big guys. And computers being located close to the manufacturing floor finally is a reality, and edge computing has come of age. Example of a modern edge computing data center. Okay, there are companies now which would contract with a manufacturing company to come and put in their edge computing data centers. They will put it in, they will manage it, they give you an SLA for it, and all you have to do is load the appropriate applications in there, and they take care of the whole thing. So that is a market that is becoming slowly increasing. So what are the elements of edge data center design? I have listed in a whole bunch of these, and I know that I'm coming up, I already exceeded the hour by 5 minutes, but the entire presentation, including the video, will be available for you folks, and I'll send it over to Hariharan, and you can take it and go through it. So I won't go through the elements of data center design.
So you can take your time, sir.
Okay. Okay, all right, very good. Thank you. Okay, edge computing, a customer's perspective. Okay, this is what a manufacturing, companies, customers are looking for. Okay, they want to be able to connect to a multitude of networks, and they will specify what those networks are. Primarily factory floor networks, and by the way, there are quite a few legacy networks still running in manufacturing. See, that's another angle which a lot of people find it difficult to deal with. Manufacturing companies cannot throw away, the machines and such other things that they have, because those are producing good products, good parts. If somebody wants to come and do an IoT project, you cannot tell them that, hey, change the CNC. You have to come up with appropriate mechanisms, okay, which can take the data, convert it to the appropriate, protocols, whatever protocol translators and so on you would have to use, and digitize the data and bring it all into an edge computer. See, the first step of digitization is to bring the data into RAM memory. That is what I tell people. Simple. You must digitize the data and bring it into RAM memory. So by that I mean, even if it is an analog control you're doing, there is a temperature controller, and there is analog coming in 4 to 20 milliamps or 0 to 10 volts, and that is being converted, into a number. That is the digitization I talk about, and that is what everybody should understand it as, converting an analog value to a number. And there, when you convert that, you go through things, such as round off error and accuracy. There are two things that you need to worry about, especially this happens during scaling. And a lot of people don't give that much attention to some of these things when they digitize, information. Then what happens is, when they start to operate on the digitized information, the error continues to creep up, simply because these two sources of errors, accuracy and round off, if you don't do it carefully based on what is it that you're measuring and the scaling you're using, you could be in a lot of trouble, and particularly in large, continuous process plants, you could be producing things not at the most optimum level because your control system is not done properly, on the system side of things. So that is just a little side conversation over here. Branch locations, okay. So what is the motivation for a lot of companies to put in edge computers and edge CPUs? Just as a sample over here, I pulled out an article from which they had discussed what is the latency and its contribution towards losses. Okay, content providers. See, one instance of buffering, that is, if you're looking at somebody's, let us say Netflix, you're watching movie, or Amazon Prime, those are the content providers. And if every so often it goes into this buffering, right? You hate it. You're watching a movie and suddenly it says it's buffering. 39% decreased in video consumption. You see that? That is lost business. So in Netflix, they have their servers located in a lot of different places close to their customers. And again, there are technologies on how you deliver, the content to different customers of yours, not from a central location. And they monitor the latency very carefully from their central control rooms. Like that, it goes down, virtual reality and gaming. If there is a 10 millisecond latency, it causes motion sickness to customer. I don't know about that, but I suppose somebody has done some tests and found out that it does happen. So it goes down the list. Online retail, if there is 100 millisecond latency, you lose 1% of sales. Okay, it goes down the list. So in other words, you cannot have these delays, And by the way, I'm sure that people who used to call United States or call from the US to India during the days of satellite communications, you talk something and there is a delay, and the other party talks something, and both of them, end up talking at the same time. So both have to back off or have a predetermined, set of rules. I will continue to talk, and when I'm done, I will tell you I'm done, then you talk. And it was such a nuisance. So once fiber optic came into being, all the undersea cables that were laid, conversations between people was a lot more tolerable. Now, nobody uses satellite communications for voice. It's purely for data. All right. I'm coming close to the very end here. I don't know how many people have read the book Flash Boys by Michael Lewis. This book is about high frequency trading on Wall Street. And by the way, this was the book about how somebody decided that if they can shave a few milliseconds off, you know, on how quickly they can get some of the pricing information from Wall Street, then they had the advantage. So one of the things that many people used to do, I don't know whether it's allowed these days, is they had co-location of their edge servers at Wall Street. So in other words, if you located your own server, which received data from Wall Street's or NASDAQ's computers, okay, which on which the trading was happening, 10 feet away, if your computer was there, that was just a Ethernet cable. It eliminated a lot of the latency. So you were able to get the data, that is at what was the pricing of some security or something that you wanted to buy. You got it a few milliseconds before the general population got it. And there were a lot of folks making millions of dollars of high frequency trading on Wall Street. Okay. And one company actually wanted to lay fiber optic cable all the way from New York to Chicago. They completed it. And they completed the fiber optic cable laying just to shave off something like 4 milliseconds. And by the way, when they finished it, somebody came and put microwave towers, line of sight microwave towers. And these guys had to drill through mountains and so on. And the line of sight microwave towers came and beat these guys to it. They were a lot less time. Their latency and delays were a lot less than this. These guys wasted about $250 million or so. So that is simply just an example on what milliseconds can do. And by the way, in the robotic example I gave you guys, every 2 milliseconds, each axis servo motor was updated with a new location where the combined axis rotations have to go to, which was what's called the what do you call that, tooltip position. Okay, the robot had 7 axes. Every 2 milliseconds you updated the position of all 7 axes, and you continued in that manner. So in those 2 milliseconds, if the robot was not where it was supposed to be, we were monitoring that too. And if the what is called the lag, there is a lead lag or the following error, if it exceeded by a certain limit we established, we would shut it down and go and check, the axis, whether the binding was there on the bearings or whatever. In fact, those are the principles we use today in the artificial intelligence, a platform that we have developed and we sell in the company that I work for and manage. So what can a few milliseconds do? They can do a lot. They can give you millions of dollars in high frequency trading, as well as destroy a whole bunch of robots and a bunch of cars for you. So now I'm looking at a new architecture without the divide. IT and OT have to work together. And by the way, there are computers today which can survive the plant floor. They can operate at 50 degrees Celsius, or even some of them can operate at 80 degrees Celsius. And the power of these computers are enormous. There is no reason that the PLCs need to be PLCs anymore, because like like any computer, the internals of the PLC, it has a CPU, it has memory, it has cache, it has everything, and the whole thing is solid state. The only thing that differentiates a PLC from a PC or a computer is the software, nothing else. So if you can, let us say that you have taken a computer and you load the computer with an operating system that does not permit a whole bunch of other services and such other things, but the OS, there is only one thing that it does. It'll execute the program scan and look at the IO scan, execute the program scan, execute the IO scan, and now you've gotten a PLC. By the way, in China, in Shanghai, in one of my travels, there are companies who sell to you. You want a Siemens PLC? We can go and buy it from Siemens at $20,000. They will also sell you a Siemens-like PLC in which you can load the Siemens own software package and run it, and it'll do the, exactly the same thing as what a Siemens PLC does. But anyway, if the Chinese can do it, you can see now where the technologies have come into. The only reason why the Rockwells and the Siemenses and the, those guys, the big guys on the automation side, seem to be able to carry on and survive the onslaught of the IT folks is the installed base. I told you, right? Legacy systems. The installed base is why they are there. Any place where it is a green field, the competition is fierce these days. And prices seem to be coming down tremendously. Okay, so coming back to the IoT architecture without the divide. Data acquisition at the top, if you look at it, the data acquisition consists of, from your left-hand side, the sensors, information coming from the sensors into the PLC if necessary, or it can go directly to an edge device, and from the edge device into an IoT gateway if you need it, and then into a cloud gateway if that is where you want to store data. See, right now, a lot of the manufacturing companies, they use the cloud to store the data, okay? But they don't use the cloud to really process anything like an MES or something of that nature. And serverless computing and most of those technologies are all coming up now in a big way. And there is also this blockchain, which is again, a new data manipulation technology for security is coming into vogue. But overall, I would say that moving forward, the data acquisition side of things is very critical, and it has to be done in an extremely proper manner. You cannot have data coming in which is wrong or any interpretation, mistakes that happens along the way. The reason is, again, if a mistake were to happen, either somebody dies or machines, will fail on the shop floor. It is that serious, and people have to keep that in mind when they are planning as well as executing on shop floor systems. Okay. So IoT architecture without the divide, it's pretty straightforward and easy. And this is a very generic architecture. This one is with particular companies. This is with Azure IoT Hub and Azure IoT Edge. And again, there are a lot of applications and services and such things coming up, coming up in the IT world. Competition is fierce. Cloud wants to take over some of the services which the edge can offer. And for example, look at that, the OPC wrapper, Azure Device SDK, Node-RED, that's an open source, which is being used now by quite a few people, small scale, but again, competition is fierce, and there's a lot of people, and the entry to to doing something in the IT field, it's a very small penalty. Everybody in their garage is able to open up a company and do AI, machine learning, and everything in between. But it is good though. It is because the cost of entry is very low. Many countries, all you need is good brain power. Like in India, we have a lot of good brain power. All we have to do is use it. Capital is easy to get these days. All right, that is going to be my end of my talk. The next chapter is to be written by today's attendees. The next era is going to be on 5G, cloud, AI, virtual reality, digital twin, Industry 4.0, smart manufacturing, you name it, and the list goes on. So you guys need to write that chapter. My time is to give to you guys whatever I know, whatever I have learned, whatever I have done. Hopefully I have done that today. And if you have any questions, we can start now.
Thank you very much, sir. That was indeed
Thank you.
a fantastic session. Since we have 10 more minutes, I would request, I think we can extend it for another 10 more minutes. So if time permits for you, we can extend it up to 11:40.
Oh, we can do that.
Yeah, thank you very much, sir. We can start the questions, Q&A sessions now. And
Mr. Vijay, it was indeed an excellent session. One question I have is you mentioned about the architecture today that is evolving.
Yeah.
I see one area is the SCADA, and we also have companies which are using Node-RED-like programming, which can directly connect to the PLCs using their device. They write software for that, like companies like Litmus or Kepware, or any of these companies. They bring their own device interfaces. Now,
correct.
With this happening, where do you see the logical growth of SCADA? If, for example, Ignition also has got Ignition Edge now. Now,
yes.
Now in this kind of a convergence that is happening, where do you see the role of DCS and Ignition and SCADA?
Yeah, SCADA basically. What is SCADA? You have to look at that very carefully. It's supervisory control data acquisition. Okay. Now, that was the realm of the shop floor, again because of the timing issues. Okay. Supervisory control was near real time for us, and in order to operate at the near real time, it had to be on a shop floor, and it had to be on a computer. And again, there are Rockwell approaches using PLCs, for DCSs and so on, but that is not necessary. Now, when a cloud and other things come into the picture, and when they claim and they can actually prove some of the speeds and latencies, you can run SCADA from a cloud, okay? But until the reliability and the speeds and such things have been proven, I would be extremely cautious. And then using device drivers and other protocol converters and so on, one of the things you run into is the fact that if there is a change done on either side of what it is connecting, you will have a problem, because these types of programs, unless it is documented, unless it is written in a way that people can take it and change it very quickly, that is going to be an issue. See, these are the disciplines IT has come into the shop floor and given us. That is revision control and version control. IT does it in a very strict manner, and see, when Microsoft ships out an update for you, automatically it gets downloaded, and you choose to update it. You do it, and they tell you within the time frame, and they have tested it. The interoperability of that update is tested across many different platforms and so on. These are all the IT, rigor and discipline coming into the shop floor. And the guys on the shop floor are also bucking the trend. They don't want that, but it is necessary as we go along to do those things. So that's my answer.
Yeah, thank you. In fact, I completely agree with you that to manage this multiple devices, the version control, revision control, that becomes a problem. That is what companies like Litmus are doing. They bring an element called Edge Manager. The Edge Manager manages thousands of devices, gateways, and it manages these version control and revision control on the fly. So that is one part. The second part is, does SCADA really have a usage in discrete manufacturing? Because you don't really need real-time monitoring in many situations.
See, what has happened is there has been a mishmash of terminology. Okay, what is manufacturing execution system? It has a little bit of SCADA in it. It has a little bit of real-time control. It has a little bit of data processing. It has a little bit of a lot of different things. Okay, which is what SCADA is also all about. That see the entire shop floor is getting a rethink today. And the way it is getting a rethink is some of the practices in the ERP world is coming down. For example, concept of master data. Okay. Master data ideas and concepts are there in the PLM world. Okay. Product lifecycle management.
Yeah.
Now, what happens is in the manufacturing execution system, that is the shop floor, there is a lot of data, which is being generated by a lot of different devices, but calibration information, nobody knows, who's got the calibration information, or it has to be managed very carefully. How do you calibrate, a torque runner? How do you calibrate, maybe a laser measurement system? So anything that is termed as master data must reside in one place, and it must come down as required. And you need separate applications for that. Okay. Like that, there are a whole host of other issues, and there is a complete rethink on manufacturing because of the fact, like I said, databases can run in memory. You don't have any issues about speeds and such things, read writes. Otherwise, what will happen? You lock you lock the database because you're reading it or writing into it, and some another process has to wait for it. It's a mess. But today, things move along very nicely, and that too, it can scale to very large, extent and sizes. So that's what my answer would be.
Thank you, sir. There's a question from my side.
Okay.
Why is Ubuntu the most preferred OS for edge devices?
Oh, you mean, I see. Okay. Ubuntu, right? That is an open source OS. And there is a lot more people who understand that, who are particularly from the plant floor side. I personally have not used any of these, okay? In-memory databases or OSs. So I'm not completely qualified to tell you that. I have heard about Ubuntu being used in many places, and the fact that it is bug-free and it is being maintained by somebody, like Red Hat was. Red Hat, Red Hat Linux, purchased by IBM for some astronomical amount. And by the way, I don't know who owns Ubuntu, but that's my answer. It's not a very good answer, but that's what I can tell you. And one thing you have to understand, in my 40 years, I have seen a lot of different OSs, coming from a lot of different companies and people. They all take, a Linux or a Unix, and they will tinker it for that particular usage, and then give it a name, and then it'll come out. And by the way, if you are in the market, go and collect something, you must know your requirements extremely well. And by that, what is it that you're doing in your business from the manufacturing side of things in its entirety? Then that should get translated into a set of specifications. What do you want the OS to do? And then it must meet all the other criteria such as who's maintaining it, how you get support for it, SLA requirements, all kinds of IT things.
Thank you, sir.
Mm-hmm.
I think Jaiharan, any such questions if anybody has, I think probably they can put it in the chat box, and probably we can try to request Vijay to provide these clarifications in the chat.
Sounds good, sir.
Okay.
So there are no other questions.
Sir,
Maybe you can give a summary, and we can close this.
All right.
sir, I'm Prasanna this side.
Yeah.
Actually, some systems are like a monopoly kind of a thing, and they don't support any protocols and all. How to integrate those systems? For example, it's a chromeleon which connects to this HPLCs, gas chromatographs, liquid chromatographs. So they controlled through this chromeleon for analytical instruments. They
Yes.
don't support any protocols to share the data, whatever they analyze and take it. In your experience, how did you what did you suggest, like how to go ahead and take the data out from them actually?
Okay. I'll tell you what. Those are the headaches of legacy issues and companies who are out of business, right? Probably
Yeah.
I don't know if those guys are in business or they're out of business. Probably out of business, right? So
Yes.
yeah, that is definitely a problem, and you would have to really narrow down the kind of data that you are trying to collect from that, and sending data and trying to control that is out of the picture because that would be too much of a headache. Collecting data is at least uh, non-threatening, means you're not going to cause any damage to the system. It's a passive operation. You would have to somehow manage to do that with discrete. Okay,
Okay.
that is the only way, and we encountered that quite a bit actually on the robot, right? Robot Sentinel is a product we have in the AI business.
Yeah.
Sometimes the controllers, from Fanuc, for example, Fanuc has a mechanism where you can tap into the controller for the axis current, how much current is being put out, because the axis current is proportional to the torque on every axis. Okay? So if some robot manufacturers, they will not give us access to the controller. So what do? We put current meter on each axis, and we know exactly where the points are, where it has to go out through the connectors, and we tap into those points for taking the measurement of the current. I mean, it's a bit risky, but that is the best. There is no other option.
Actually, I think like what you have said, sir. If I may add, also saying that some of those parameters, whatever you wanted to read, you may have to tell these people and then try to take it through your RS-232C or any of the protocols, and then try to see whether you can read these data. That's the
Correct.
only thing which is possible. You will not be able to take the 100% of whatever the inside LC or GC.
Yeah, precisely, because even with the legacy equipment, a day will come when you would have to buy brand new. Even with these CNC machines, there are 25, 30-year-old CNC machines still working, and they'll still work. But when all the people who are maintaining it and managing it, they die off slowly. So what do you do now?
Correct, sir.
So that is what the issues are. So, but slowly the transformation is happening. People are
Yeah,
dealing with these types of issues in the best way possible.
in fact, that is what Mr. Vijay, I came across a company called Litmus Automation based out of US, and they have built drivers for company of equipments built as early as 1960s. So
Yes.
any device, they have built a driver, and they are saying if you don't have, they will build it within 2 weeks' time. So
Yeah.
that's a kind of interface happening now.
Correct. Because I'll tell you what, in those companies, there is probably an old guy who knows RS-232 backwards and forwards.
Correct.
Okay.
Correct, sir.
And he knows printer parallel interfaces and whatnot, RS-485 multi-drop. He knows all these things. You tell me, how many people know today? Youngsters.
Yeah.
They
That's
won't.
why these companies are coming as a product. They build it as a part of the product, and they keep on updating it. So they have thousands of drivers available to them,
Correct.
which they can share it across various customers.
Yes. I mean, these are niche market people, and they have something useful now, particularly in the days of IoT, right? They are able to help us to collect the data and put it out onto the edge controller or out to the cloud and do whatever else we want to do with it. And I would say that's a good one, good something to be doing in their retirement.
True.
Correct.
Why not?
And,
They have
Vijay said there are a lot of requests about
Yeah.
digital twins
Yes.
and cyber security
Oh.
and edge computing and cyber security. There are a lot of chats requirements which are coming up. I think
Okay.
probably we'll have to look at it the next level of discussion, sir.
Oh, absolutely. Yeah, you can, collate everything together
Yeah,
and send it to me, and I will reply back.
absolutely, sir. Sure.
Sure, sir. Sure.
Because,
Thank you, sir. Thank you, sir. Thank you.
yeah, and again, the field we were discussing is so wide. Security, okay, is so important and critical. I didn't even touch upon security because I thought there was a whole bunch of other stuff I need to touch on. The
Yeah.
entire evolution aspects of how we came here.
Yes.
But one thing I can tell you, IT and the products that IT has today, that is coming into manufacturing in a big way, and nobody can avoid that. Nobody can get out of it either. So, but this will be something for the IT folks to play in, as long as they are receptive to the dirty environment or the hot environment of manufacturing. They shouldn't expect to sit in AC rooms.
That's a hard thing today to have automation engineers to get their hands dirty.
I know.
Yeah. So we used to call the American used to call white collar and blue collar.
That's
So,
right.
so all the youngsters, they want a white collar, not a blue collar.
Right.
Yeah.
Yeah. I mean, we have a severe problem here too. With all the automotive companies, nobody wants to stay.
So we are close to the time, and maybe we can take one last question from any of the participants if they are interested, or we'll close the session. The closing remarks. Anybody take on any questions? Sir, you can give the closing remarks, sir.
Okay, you want me to do that?
Yeah, you can do that, and I also have some set of closing remarks. We can do that after you.
All right. I mean, I don't know how many people are still there in the call, but all right. Uh, hey, this is Vijay Rangarajan, from Los Angeles. I'd like to thank everybody who attended, the call today, and hopefully you all had something useful that you learned from this. I know that this was at a much, I kept it at a higher level. I didn't want to get into a lot of details about protocols and the mechanics of how a computer works or a processor and a CPU. Okay, sorry, a controller and a processor and a CPU. What are those differences? Why do they have different names? Anyway, these can be part of another conversation another day. Hopefully, this is not going to be the one-time affair. There are many subjects that we can discuss and talk about, and I'm ready to do that and ready to contribute whatever we can to India. That's all I have to say. I'll turn it over to the organizers now. Go ahead.
Thank you very much, Vijay sir. It was the session was nicely articulated, and you had taken us through the minuscule levels of processing. Okay.
Mhm.
Yeah. So that's we had simplified a lot of things. Particularly, we like the way in which you articulated what the protocol means. And we also learned a lot about the disruption in the automation pyramid, where we see now that the sensors, not only the sensors, the level 0 to level 4, if you take, all the levels now get disrupted in the automation pyramid.
Yes.
And over to now, we are in a space where we try to use a lot of open protocols. Ethernet has really disrupted, and it is becoming more and more deterministic. And we are in an age where we are trying to use open protocols like OPC, and even the programming softwares. If you take PLC programmings, there are like open source programming softwares like Codisys coming in, which is really disrupting the world.
Yes.
And apparently we have got a very good understanding of what edge means, right from your 1970s to 2020. That's it from my side.
That's right. Okay, very good. Very nice.
Thanks to my executive committee, and very special thanks to Mr. Gopinath, who had really identified our speaker for the day. And it was really an enchanting session, sir.
All right.
Yeah, thank you, Ravi, Vijay, and then Gopi and Jayaharan. The thing is that you have taken your time. I think now the time is around 12 o'clock there in Los Angeles.
11:15.
11:15.
Okay, 11:15. Okay,
Yeah.
right.
No issues.
So the late hours you could spend for us. Thanks a lot for this, and then we hope that we meet again, and we welcome you also when you are available at Chennai. We'll have a session on face-to-face with the program.
Definitely, we will do that.
Thank you, sir. Thanks a lot
Thank you so
for
much, sir.
sharing.
Thank you very much. Thank you all for participating in this webinar.
Yeah.
Thank you.
Good night.
Thank you, Mr. Sai
Thank
Ramesh
you.
and
It was good.
Jayaram.
Yeah, thank you.
It was an excellent session.
Thank you all.
Thanks, Jayaran. It was good.
Thank you, Mr. Vijay. Have a good
Thank you.
sleep now. Have a good weekend.
Yeah.
Okay.
Jayaran?
Yes, I am there, sir.
Yeah, now that chat box you can take, and then you can take those questions and see whether we can send it to Vijay, and then try to see whether we can close it.
Yes, sir, very much.
Right.
Thank you.
Thank you.